Alright, so let's go over this little graph here and try to run Prim's algorithm on it. Okay, so Prim's algorithm basically runs on undirected weighted graphs, where the point is that we want to essentially find the minimum cost spanning tree. So minimum simply means that we want to try to minimize these edge weights. Spanning trees are essentially trees that do not have loops inside them. So like here you can notice, you have A, B, D, G, F, that is a massive loop. You have B, D, C, which itself is a loop. You have D, C, E, G, which is a loop. F, E, G, which is a loop. You basically don't want this. You want to make it sure that you have all the vertices, but you don't have so many edges, right? And the general idea is, if you have n vertices, you basically want n minus 1 edges. That kind of is the idea. That is basically what you're trying to do. Otherwise here you have too many edges. Basically that is what is happening. Okay, so the way Prim works is that Prim starts on a particular vertex, and then based on that particular vertex likes to grow outwards. Okay, so let's actually run it. Right, let's run it on like couple of different points, and we can see what happens from there. So Prim of let's call it on A. Let's be that way. Okay, so let's call Prim on A and let's see what happens. Okay, so when we start Prim on A, we notice that we have two edges that we have discovered, which is AB, which is cost of 7, AF, which costs 11. So clearly we'll take the cheaper one, which is AB, which will cost 7. Awesome. Now we have opened some more options. So we still have AF, which costs 11, and we now also have the option to open BD and BC, right? So BD costs 11, BC costs 12. Now since there is a tie between AF and BD, I'll simply open AF because that's how I want to do it. That's how I want to break my ties. Okay, so that is what we will get. Now since I have opened F, now I have many different options. I can either go with BD, which costs 11 still, BC, which costs 12. I can also go with FE, which can cost 10. I can also go with FG, which will cost me 12, right? So again, our task is to minimize basically whatever the edge weight that we pick, and to also ensure that there are no loops. So we can add FE because FE is actually very cheap here. So we'll just add that guy at a cost of 10. Amazing. Now let's check what our options are again. So BD at 11 cost, BC at 12, right? CE at 8, CG at 7, FG at 12. Now clearly you can very easily see, I think, that EG is in fact the cheapest option. So we'll just open that. Okay, now we continue. Okay, so also notice that we still have some vertices that we have not connected yet, so therefore we have to keep the process going. Again, the point is that we want to have every single vertex possible, but we don't want to have any loops at all anywhere. Okay, so now notice E to C will in fact cost me 8, G to F will cost me 12, but it will basically be causing a loop. Therefore I will never be basically picking FG, because if I actually add FG, it becomes a loop, and we do not want that. So therefore consider this one completely gone. FG can never be added to this spanning tree that we have started to create now. Okay, let's continue then. So E to C is maybe possible, but so that costs 8, right? And I think the rest of the options are basically the same. Nothing much has changed essentially. So I think since adding EC does not necessarily violate anything, we can just add it, right? It will cost 8. Okay, now once EC is added, you can notice that the only vertex that we are missing now is essentially D, right? And the way we add it kind of matters, because if you add BD, like look what happens. If you add BD, it becomes a loop, which is a problem. So essentially we cannot add I mean it was like this, right? If you add D, it kind of can become like that, but that is only if you add the vertex, right? I kind of missaw the diagram because of how I've extended C, but yes. So if you add a BD, it costs 11. If you add a CD, it costs a 10. If you add GD, it costs a 9. So clearly I think we can just pick GD, which costs a 9. So A, B, C, D, E, F, G, and this basically is the spanning tree that we have. This is the spanning tree that we got by running Prim's algorithm on A. And just to be kind of a bit rigorous, let's run it on just let's run it on another vertex, just to be sure about how it actually runs, right? So let's do that somewhere over here. Let's keep this graph here this time. and let's run Prim's algorithm on let's take C, or no, let's take D actually, right? No specific reason, I just want to take D and run things on it. So D has three major edges that are coming out: CD, which costs 10, DB, which costs 11, and DG, which costs 9. So clearly it will go for DG, which will cost a 9. Then what will happen is that GE will open up, GF will open up, and it still has the other things, but clearly GE is the cheaper one. It costs 7, so it will simply open that, right? So you have 7 here. Now again, GF is open, but it costs 12. Then EC has opened, which costs 8, which is extremely cheap. So I think we should actually be opening that. If you compare everything else, EC is actually quite very cheap, so we open that, and yeah, that is basically added. Now notice that some EC, right, that is C. I didn't write that properly, but yeah, okay. Now notice that you can never add CD anymore, because if you do that, you basically end up with a loop. So therefore it is best to be careful here, right? So now the options that we have are EF, which will cost a 10, FG, which will cost us a 12. So I think EF seems kind of okay, but let's keep moving. We have more edges to consider. DB, which will cost 11, CD, which will CB, which will cost 12. But clearly I think we can see that EF is in fact extremely cheap, so we will add that, right? And then I think you can see that even with F added, AF, G, you can never add FG now, because if you do that, you will now end up with a loop, and clearly we should not have any loops. So that's there. And then let us see what else can we add here. So I think the only vertex that is missing here is B and A, right? Okay, so let's try to move towards those guys specifically. So you can get there through CB, which costs 12, I think. Our other options don't seem that great. CD would be 10, which we cannot add. So yes, it does seem that we would actually have to add B through C. So CB at 12. And then of course when you add this, you can simply add AB, right? So AB, which becomes a 7. Now you can very clearly notice how this whole diagram has become quite different, right? You will notice that earlier in this Prim's A version we did not have BC edge, but in this Prim D version we actually do have an edge here, right? BC edge is in fact present, right? You will notice these kind of small little changes that have actually happened, right? And some things that have kind of remained the same, maybe for arbitrary reasons or because we started at a certain configuration. Like CD edge is missing in both the versions, and FG was not sort of connected in both the versions. So that's basically how it is. And the point is that if you run Prim on all the different edges, you will basically get different versions of the MST. Most of them will probably share a lot of common edges, but the point is that in the end you will have this kind of a graph with every single vertex present, A, B, C, D, E, F, G. Like basically every vertex will be present, and you will only have number of vertices minus one number of edges present in the graph, right? That is how you create a minimum cost spanning tree using Prim's algorithm. So that's about it. Yeah, pretty simple.